So this should be a nice, simple problem or way of looking at problems to do with impulse and momentum. I hope you're still familiar with the idea of impulse as being change in momentum, and the idea that change in momentum is caused by force which is applied over a certain period of time. If we know the size of the force applied, we know how long the force will be in contact for, we can predict what the change in momentum will be. Conversely, you often see impulse in collisions where something comes to zero, and so we know what the size of the change in momentum is, and we look at the size of the force applied. So an example of a person hitting something. So initially the ball's coming towards them with a certain speed and direction. It's got a certain amount of momentum. Now, after we hit the ball, it flies back in the opposite direction. It's changed its momentum. In fact, it has gone from all this momentum this way to all that momentum that way, and we're going to draw vector triangles to do it. Now in this case, obviously, it's not going to be a vector triangle, it's going to be all in one straight line, but if you remember rightly, it's going to be final, there's our momentum afterwards, minus initial. So we flip our initial one over, and here we have our total change in momentum of the ball. Okay, and we can think about, well, where did that momentum come from? It came from the bat. How did the bat get that momentum? The person was swinging it. How long was the bat in contact with the ball for? Once we know that, we can work out what force the person must have applied. Obviously, with a hard ball and a hard bat, it's going to only be in contact for a small amount of time. There's going to be a minimum amount of squishiness and elasticity. There'll be large forces, and therefore there'll be large changes in momentum. You could have something that was moving towards you very, very fast, like a cricket ball, and you could belt it back in the opposite direction just as fast. On the other hand, let's say instead of belting it back towards the direction it came from, you changed its direction. You would still use this kind of vector triangle. Let's say instead of going straight back, our after now has been sent at 45 degrees. There's our after there. Okay, and we're still minusing our initial. There's our initial there. We can say, well, this is its change in momentum. It's now moved it in that direction. And you're all familiar with hitting things with bats. Cricket balls, tennis balls, badminton, shuttlecocks, I don't mind. You've hit things with bats and you've seen what direction they fly off in. You've seen that you can change the momentum in a variety of ways depending on how you hit it, the direction of the force, the size of the force, the length of time you're in contact with the object for. And that's what momentum's all about. Now when we come to changing momentum in 2 dimensions, we are going to do a few exercises on that, but I'm going to let those wait and do a worked example to show you that 2-dimensional change, and also a little bit more detail about these vector triangles or vector diagrams.